So we are given this bridged ketone which is reacted with hydroxylamine. We know that hydroxylamine reacts with any carbonyl, just happens a condensation reaction giving to us Schiff base product. So let's just write it. So now we got a NOH, acid chloride is given as a reagent. So this is just acetylates the alcohol group, nothing else. So just let's write the product. So after writing the product, we can see that the acetate group converts into good leaving group. Now here comes the original fragmentation reaction. So what happens, one of the bonds which is connected to a C double bond N bond, so that's just fragments. So there are two bonds, so there are two possibilities. So let's just find out. So I am rewriting the intermediate. So now here we can see that in the intermediate there is two possibilities. One is that this bond and one is this bond. So let's just find out which is the more favorable for the reaction. So now we can see that if this bond moves, so we get this intermediate. So just this bond moves here, forming C double bond N, and acetate and cleaves. So we get this tertiary carbocation. Now if this bond moves, so we get, now we can see that this is 3 degree carbocation, this is 1 degree carbocation. So obviously 3 degree carbocation is more stable. So reaction proceeds via 3 degree carbocation intermediate. So let's just redraw this into a more simple form. So I am just writing the 5-membered ring at first. After that the groups are attached accordingly. So there is a positive charge. So we can see that at only the other end there is one hydrogen which can eliminate, giving leading back to a formation of a alkene. So this is our product. So this reaction is called Beckmann fragmentation. This is nothing different like a Beckmann rearrangement. Just here what occurs that during the rearrangement a bond CC bond cleaves. So this is that is why it is called Beckmann fragmentation. So our next example, this is diol. So what happens, at first one of the alcohol groups are protonated, converted into a leaving group. So what we can see that there is another alcohol group which just acts as a electron donating group, so that the lone pair of the oxygen just pushes back to the carbon, and the bond attached to carbon just cleaves, leading to a formation of a C double bond C, and from that the other attached the water molecule just leaves. As this is symmetrical, you can just draw the bond cleavage other way around also. So here we got the product. Now this is our product. This starting material which is reacted with a acid. So at first we all know that what happens, that here is a carbonyl group is given. So acid first protonate that carbonyl. So after that what happens, the carbonyl converted into a good electron sink. It can withdraw electron density from the ring. So what happens on the other way around, there is a electron donating group which is OMe. So the lone pair on the oxygen just pushes back to the ring, and we also know that there is a junction of 5-member and 4-member ring, so it is not very stable, and also just due to the presence of one electron donating and one electron sink, this is more vulnerable to exposed to a ring expansion. So what happens, the lone pair of the oxygen just pushes back to this ring carbon, and the bond with the ring carbon cleaves back to another bond creating a C double bond C, and the carbonyl group cleaves, forming a OH. So we got a ring expanded product, but we will write in simple form. So there comes C double bond C1, the rest will be as it is. There will be a double bond ONE, which will be later hydroxylated. So we can draw now. This is a 7-membered ring, so we can draw in a expanded form a proper 7-membered ring structure. This is also much more tautomerized into a more stable carbonyl form in the 7-membered ring. So now this oxygen pushes back, this OMe gets back, because our OMe is a good leaving group. So we got this 7-membered ring. This is an isolated ketone, diketone you can say. So after that, our next example is something like the previous example, but there is a trick. So here we can see that there is a 2 carbonyl. For one carbonyl there is a alpha position, there is a 1 OMe. So the first question will be which carbonyl will be most predominantly protonated. So then this is the more thing, because that will be the electron sink, and from that point then bond migration or bond cleavage occurs. So that is a more question, fundamental question. So what we can see that in the alpha position there is a OMe. So if that carbonyl is hydrogenated, hydrogen bonded, so that will also be stabilized by the neighboring OMe group. So in rough we can write the probable hydrogen bonded form. So if there is a OMe group and the ketone is protonated, then the neighboring OMe group can stabilize further this hydrogen bonding. So the hydrogen bonding will be favorably at that position, not the another carbonyl. So the reaction will proceed via that center, that special hydrogen bonded carbonyl. So this phenyl group is nothing, participates in the reaction, so we are not considering that. So just I am writing that protonated carbonyl, and the rest thing is similar. Now we are the lone pair of the OMe group. This is just pushes back to the ring carbon, and one of the, as this the valency of the carbon exceeds to 5, so one of the bond attached to that carbon should be cleaved. So which bond will be cleaved? So that will be reacted to the protonated carbonyl carbon. So there is a chance that this double bonded carbon will migrate, but that will leads to a double bonded carbocation, that is a phenyl carbocation, which is very much unstable. So that bond will not be migrate or cleaved. So the other bond, which is this, so this will cleave, so there will be no harm to that. So that bond will migrate. So the OH bond, so we get this intermediate. So now we got this intermediate. So as we know that double bonded OMe is just hydrolyzed with the water molecule in the reaction medium that will convert the ketone. So I am not writing that here. So I am just rewriting that product into a simple good form. So what we got, this 2 5-membered ring junction in the proper orientations. So we got our product, and in the ring junction there is a OH. Both the examples are very similar, but for the second example there is one trick, key aspect, that which carbonyl we want to protonate. So just because of the obvious reason of that, this is a carbonyl which we protonates, that will lead to a more convincing product. So you can try by yourself to protonate other carbonyl and try to form a product, but we will not get a feasible product out of that. Okay, so this is the possible explanation for this reaction. This is our starting material, which is treated with a base OH minus. So we all know that what will happen, that there is a nucleophilic center which is carbonyl center, so the base will automatically attack wherever at that center. So we will get this intermediate. So after that, so this OMS group is nothing but methyl sulfonate, which is this group. So the OMS group is very good leaving group. Therefore, this O minus pushes back to this carbon. This bond goes here, and this goes back. So there is minus OMS, and we get our product. So you can simply write that. Okay. This has been given. So here a formic acid is given as an acid, which is a very strong acid. Organic acid, of course, moderately strong with respect to organic acid. So they will put on this alcohol and convert it to a leaving group. So here you can see that this is a electron bonding group, lone pair pyrrole. So that will push back here, and this bond will come here, and this will be acts as a leaving group. So the ring will be broken. So for simplicity, we will write at first the exact ring with the modifications, which is here a double bond will be formed. This part is intact, this part is then double bond connected. So this we can rewrite. You can see that this is a 6-member ring. So at first we will write it 6-member ring. There we place this double bond here. This two double bond, another allylic bond is connected. After that, other side of this there is a double bond OME, which is connected to this portion. Here is a methyl, and from this position there will be this part, which I write like this. So here what happens, curtain formation. So ring migrates through here, this comes here, this goes here, this comes here, this, what we get, this will be conformations. So after the medium there will be an anion, which is formate anion, which will attack here. So we get, this will be again in acidic medium. This will be converted in tautomerized form, will be in a keto form. So in a nutshell we can rewrite it. This goes here, this goes here, this goes here. So we get this product, the formate, and then attacks here. And there is a small example which is left. Just give it a try. I am not writing it. You can solve it easily by yourself after watching all these examples. Base. So base will be like OH minus, like something, which will just deprotonate it, converting into a O minus. So we know that OMS is a leaving group, good leaving group, which is a methyl sulfonate. So what happens is pushes back this carbon goes here, this, which is like for linkage. 6 member will be the base link, and this is a 6 member. So I draw it like that. Here will be a ketone in the other side. There will be this one, this one, this one, and there will be 1 2 3 1 2 3. That will be the product.